looking now at the factors, right, that affect the rates of reaction, okay? Now, we talked previously in the previous video about the collision theory, and we agreed, right, that we need high-frequency collisions, and we also need effective collisions in order for our reaction to be successful. And as a recap, to have an effective collision, you need a proper angle and the right amount of energy. Okay, so once again, we want our high-frequency collisions and effective collisions to make a reaction successful. Now we're going to analyze what factors will increase our chance, right, of having those things. All right, no problem. So this topic, right, is very, very common sense. So you in your minds, right, should be thinking to yourselves, how can I increase the chance of getting more effective collisions? All you're doing. Okay, now what do I have here? We have a cold water bath where the ice is already melted, but you know, the water's still in there, in this test tube right here. I have a hot water bath, okay, where the water is, you know, pretty nice and hot. So let me turn it off. Bam. All right. Now, I'm going to use, guys, some Alka-Seltzer tablets that I got from my local Walgreens, no problem. Okay, alrighty. And what we're going to do in terms of temperature, right, we're going to place, right, I'm going to break one in half and then place half in each of these test tubes. And we're going to try to observe the results, okay? So we're going to try and do that, no problem, okay? So we have the colder test tube, the colder water, and we have the hotter, okay, material right here, hotter test tube right here with the hotter water, no problem, right? So in your minds, you're thinking to yourselves, right? The colder test tube, okay, the lower temperature test tube, lower average kinetic energy, right? Because that's the definition of temperature, yes? And this guy has a higher average kinetic energy. So in your minds, right, you should be guessing already or determining already which one of these guys will react faster. Okay, so let's see. All right, so I'm going to break this tablet in half to the best of my ability. All right, okay, and I'm going to put the hotter guy over here. All right, turn it like that. And then I'll put the colder guy over here. Alrighty. Oh goodness. Let's see. There we go. Okay. So once again, the hotter test tube is this one, and the colder test tube is this one. Now I'm gonna try to drop them in the same time, right? Okay. All right. So 1, 2, 3. Okay. Can you guys see that? Okay, this is the hotter test tube right here, fizzing like crazy, and this is the colder test tube right here, okay? So you see right away, automatically, right, that the hotter test tube, the reaction went much faster, okay, and fizzed out, okay? So ladies and gentlemen, okay, our expectations, you know, were proven right. The higher temperature, the higher average kinetic energy produce a chance of what? Higher frequency collisions and more effective collisions, right? So that right there, in terms of temperature, proves that a higher temperature, okay, increases the rate of reaction, okay, for most reactions. Okay, alrighty. We'll move on to another factor in a second. Okay, ladies and gentlemen, we're moving on to our next factor. Our next factor will be concentration. Now, in this test tube right here, okay, this outer test tube right here, I'm using 1 big M, 1 molar hydrochloric acid, right? No problem. And in this test tube right here, I have a very, very diluted version of the 1 molar. So I put a lot of water. I put a little bit of 1 molar, but I put a lot more water in it, right? So we're going to determine now, we're going to see which one of these guys is going to react faster when I put the Alka-Seltzer tablets in each of them, okay? So remember, what are we analyzing? We're analyzing factors that affect the rate of reaction. We're looking at now concentration, yes? Okay, so this is a higher concentration to our right over here, okay? And so lower concentration over here, okay? So this is higher, depending on your perspective, how you're looking at it. This test tube right here and the outer one right here is higher concentration, 1 molar. And this is a much weaker, much diluted, okay, concentration of hydrochloric acid. Now, once again, you should be determining to yourselves, right, which one of these test tubes will give us the better chance of increasing a higher frequency of collisions and giving us more effective collisions. Okay, so let's see. All right, so we got our tablet. Trying to break it in half again. Okay, alrighty. So I'm gonna try to put it in the same time. Okay, 1, 2, 3. All right, now you see that? This guy's fizzing way faster, rising up the tube, the test tube. Oh my goodness, it's gonna reach the top. No, it doesn't, but see that, right? The higher concentration Alka-Seltzer, the higher concentration acid, right, reacts much more faster, much more vigorously than the lower concentration one. Okay, almost feel it, testing almost jumped out of the test tube. So that's very nice, conclusive results right there. Now, why is that? You can always, right, explain the topics of rate of reactions in terms of increasing the chance of the frequency of collisions and giving you a better chance of getting more effective collisions, folks, all right? So that's factor number 2, concentration. Okay, nice results right there, no problem. So the higher concentration has more particles, right, per volume. Okay, so the chance of collisions, all right, are increased. All right, so think of a room where you got 5 students running around, as opposed to a room where you have 50 students running around. Okay, there's much more chance of them bumping into each other if there's more students in the same space. Okay, so that's concentration. Take care. Okay, ladies and gentlemen, we're back looking at the factors that affect rates of reactions. Okay, now what we're going to do this time, we have our trusty Alka-Seltzer tablets, which is going to help us out. Okay, but this time what we're going to do, we're going to crush one of them, right? So I have a mortar and pestle right here, okay? We're going to crush one of them, and the other one, we're going to put it whole into these containers of water. So once again, I'm going to put the crushed Alka-Seltzer into this outer one right here, this outer container of water, and in this beaker of water, I'm going to put a whole Alka-Seltzer tablet, right? And what we're going to do, we're going to see, right, which one reacts faster. Now, as always, you're asking yourself, you're determining, you're going to make an expectation, right, as to which one do you think is going to react faster and why. Now, I always say, let's be able now, right, since we're moving on, we're in high school now, we want to explain things, right, on a deeper level, okay? So we don't want to say it reacted faster just because of the way it was and that's it, right? We want to explain in terms of collision theory and other terminologies like that, okay? So once again, we want to explain, deeper, to the point, okay, but clear and concise. But no, we don't want to be like obvious with our answers. Okay, so let's do it. So I have inside here the, can you see it, the Alka-Seltzer pill? All right, I'm gonna crush it up. Alrighty. Make sure it's nice and powdered. What I'm gonna do, I'm gonna put it in this weighing boat right here so I can easily transfer it. Alrighty. And good. I have the whole pill right here. So what I'm gonna do, I'm gonna try as much as possible, right, to place them inside the water at the same time simultaneously. Yes? So okay, 1, 2, 3, bam. Okay, we're looking, you see that right there? How much the crushed Alka-Seltzer started fizzing up much more than the whole pill. So we see definitely, right, nice and clear and conclusive that the crushed Alka-Seltzer, okay, reacted faster. Now the question is why? Now, if they asked you, for example, on a test or a quiz or something, and they said explain, okay, you just don't want to say because it was smaller, right? Okay, that's just the surface, okay? You want to explain in terms of collision theory, guys. You want to say that, okay, in terms of the fact that the particles are smaller, they now have a higher surface area, giving, okay, the reaction of how much higher frequency of collisions. And when you have a higher frequency of collisions, guess what? You have a greater chance of getting what? More effective collisions, okay? So it's all about increasing the chance of what? Frequency collisions, and in turn, that gives you more effective collisions. And the more effective collisions you have, your reaction will go faster. So once again, nice simple demo. Surface area, okay, is the factor that we just looked at. Alrighty, no problem. This is a hot plate I have this stuff on, so it's not on. Okay, it's just for a platform so you can see it better. So once again, guys, we're moving on to these topics and factors. We're going to look at catalyst next, okay? So no problem. All right, guys, so once again, nice results. All right, take care. Okay, guys, we're moving on in our journey of factors that affect the rate of reaction. Now, right here, I have two graduate cylinders, okay? And I have inside of them, right? Each of them, I have some hydrogen peroxide. It's actually 30%, okay? So it's pretty decently strong, okay? Now, what I'm gonna do, right? I am going to add a catalyst to the outer one, okay? And we'll compare the rate of reaction as to the uncatalyzed hydrogen peroxide. Now, what's happening right now with these two containers, folks? The hydrogen peroxide is decomposing very, very slowly, right, into water and oxygen. And you know, you can't really see it or anything, but it's decomposing slowly. But what we're gonna do, we're gonna add the catalyst, right, and see the effect of when we add the catalyst to this outer graduate cylinder that has hydrogen peroxide in it, okay? So no problem. All right. Now, to get the effect, to see the oxygen being liberated and being given off, we're gonna put some trusty dish soap inside of both of them, right? No problem. Put a small amount here. And put a small amount there. Okay. I'll give it a little swirl. Give that a little swirl. Okay. Alrighty. So they both have dish soap, no problem. So we're gonna make sure that the dish soap was not the guy that caused the effect. Okay? Alright. No problem. So what we're gonna do now is this, folks. We're gonna use this guy right here. It's potassium iodide. I don't know if you can see that or not. Potassium iodide. Okay. And what we're gonna do, we're gonna make it aqueous. So I'm gonna put some in there. Okay, not too much. Alrighty. I'll give it a swirl. Okay, so what are we doing right now? We have our aqueous potassium iodide, dissolves nicely, okay, very high solubility. All right, so as we agreed, right, this is our catalyst, okay? We're gonna put some catalyst into the outer graduate cylinder with the hydrogen peroxide in it. The concentrations of the peroxides are the same. They both have basically the same amount of soap in them, okay? So the factor that we're looking at, right, is how the catalyst affects the rate of reaction as compared to the uncatalyzed graduate cylinder that has hydrogen peroxide in it. So there we go. I'll put a little bit in there. Okay, you see the color change right there already? Okay. So that's the potassium iodide. Now, it's moving a little slowly, right? But let's just keep our eye on it, no problem. It's already bubbling up here, so you can see that's the oxygen gas being trapped right there, folks. I notice this one right here is not doing anything, staying the same. This one also is decomposing, right, to water and oxygen, but as I said before, very, very slowly, right? But what's happening over here, right? Decomposition has been sped up, if you will, okay, by the addition of our catalyst, potassium iodide, okay? And if you notice, right, the soap has trapped the oxygen, okay? The trapped oxygen in the soap is moving up slowly, slowly, slowly up the graduate cylinder. Now, the thing is about how the catalyst, right, speeds up the reaction. It does something that we're going to describe later on when we do potential energy diagrams. It does something called lowering the activation energy hill. So if you don't know what that is, no problem, no stress. We're going to do potential energy diagrams soon, okay? But it lowers the activation hill of the potential energy diagrams. Okay, if you look in the other videos I made previously, you'll see I have a video on potential energy diagrams. But I'm going to make another one about potential energy diagrams, folks. So it lowers the hill, so it's easier for the reactants to get to the product side, and it's easier for the products to get to the reactant side. So the reaction speeds up. Think of it as a mountain, right? and the mountain is at, I don't know, 12,000 feet high, okay? And if you're able to lower the mountain to say, I don't know, 8,000 feet or 6,000 feet, make it lower, it's an easier travel back and forth. So the reaction gets sped up. Okay, see that? I think I gotta move it soon. I don't want to overflow on the desk. All right, guys, take care. As always, hard work plus sacrifice equals success. Nice, bam, take care.